Welcome everybody to the first day of the ISBA World Meeting. My name is Mike Jordan from University of California, Berkeley. My job today is just to keep the speakers happy, and so luckily I was given this fan, and I'm supposed to fan the speaker if he gets hot. So I will be standing here fanning the speaker. So these lectures are the traditional ISBA tutorial lectures, but they've been slightly renamed and repurposed. They're being named the ISBA Lectures on Bayesian Foundations to give them a slightly more grand title. And these are being videotaped. They will appear on the ISBA website soon after the meeting, and you'll be able to go to click there and enjoy them again and again and again. And hopefully people throughout the world will also be enjoying them. That's the whole point, really. There's hundreds of thousands of people behind you who are sitting out there as a potential audience for these lectures. So I really think this is a wonderful thing to do for ISBA. This is the beginning. We're going to do 4 of these lectures today, and future ISBA meetings we will also do this. And soon I think we'll have a large library full of great lectures that'll be watched out throughout the world. And I can't think of anything we can do to get out in the world better than this. So our first speaker, with no further ado, Ad van der Vaart from Leiden. He really needs no introduction. I teach at Berkeley the asymptotics course, and I use Ad's book. And I think it's fair to say that it's changed the lives of many students at Berkeley and led to higher quality research being done. It's a wonderful book. And Ad writes beautifully and thinks beautifully. It's really the tradition of mathematical statistics going back to people like Neyman and Wald, Lecomte, and so on. And Ad is sort of, in our generation, one of the leading members of that grand tradition. So I'm more than delighted to invite Ad up to the stage and have him give the first lecture.
Okay, thank you very much for this kind introduction. It's a great pleasure and a great honor to speak here today. And what I would like to speak about is nonparametric Bayesian statistics. And then in particular, my attention will go to credible sets and uncertainty quantification by nonparametric Bayesian methods. The layout of the talk is, well, there are 4 parts. Very brief part, I'll say what nonparametric Bayes is, and then there will be a part setting the ground for the main part, which is on credible sets in 3 and 4, and the ground part is on Gaussian process priors. Mostly what I'll be talking about as examples are priors that are Gaussian processes, but I think the things I'll say will be valid for other priors as well, even though we don't have any mathematical results on those today. You see 4 nice pictures here, and I'll explain them in more detail later. But the idea there is that we see a true function, which we're trying to estimate, and the true function is this black curve. There is a posterior distribution which has a posterior mean, that's the blue curve, and then you see something gray, and that is some indication of the posterior distribution, how spread it is. And you see that in the first and the fourth picture, it's reasonably good. Well, the first picture has a small signal-to-noise ratio, so the curve, the posterior mean, is not good. It gives only the global properties of the true curve, but at least the uncertainty margin looks okay. In the fourth, there is a little noise, and both the posterior mean and the uncertainty quantification seem to be okay. In the second and the third, you see something goes wrong. The gray doesn't capture the true curve, the black curve, and so somehow nonparametric Bayes fails, and I'd like to get some insight in why that happens and when that happens. This is based on joint work with 4 co-authors. First 3 are students. Bartek and Botond are here, also giving poster presentations. Susanne is not here. And the 4th is Harry van Zanten, well, also trying to look like a student here in his young days, but he's a bit older. I make a disclaimer, that's also because this is taped. In the old days, you just gave a talk, and then after the talk, everything was gone. You could say what you liked, and you could make some mistakes. Then you had a time of slides, and people asked your slides afterwards. You had to be a bit careful about what you wrote. And now I'm even being videotaped, so for years to come, I understand this ISBA site will show all my mistakes. I hope I won't make too many mistakes, but I certainly will try to make the statements a bit simpler than they really are, so that it's better for this presentation. So nonparametric Bayes, what's it about? We would like to estimate some function. And so if we do that the Bayesian way, we need a prior on a function space. I don't want to have this, but... and that's a complicated object. We could visualize something like that by some draws. Did I go too fast? So here you see a regression problem. The dots are data, and we would like to estimate a regression function for the dots. And you see three dashed curves, and they're actually three realizations from a prior on function space. They're rather straight here, but actually they are wiggly functions, and in the resolution of the screen, they look a bit straight. They're actually Gaussian process realizations. And this is just three draws from the prior, and you see the prior was adjusted a little bit to the data, and that the height of the curves is right, but it doesn't follow the regression curve in the data. Of course, we haven't seen the data yet when we get the prior. The idea is then that we do get the data, these dots, we get to see them, and then we update a prior to a posterior, which again is a complicated object. It's a distribution, a probability distribution on a function space. And you can also visualize that by taking some draws from it, which I did here, and you see a somewhat complicated crowd, but there are curved dash curves, and what they do is they sort of follow the data. So the Bayesian analysis was successful in that the prior, which had wrong realizations, not following the data, was updated by the data to a posterior that produces the right sort of thing. The question we'll ask is, does this indeed work? Does this give good reconstructions? So if you look at the sort of center of that cloud, does that follow the data? In this case, it does. But the more important question for today is, does the posterior distribution also give a correct sense of the remaining uncertainty in the data? Not only would we take, say, the average of all those draws from the posterior, which would be the posterior mean, and that would be the estimate, a point estimate for the true curve. We would also look a little bit at the spread in these wiggly things you see there, and we would hope that somehow that the width of that band tells you something about how certain you can be of your reconstruction. That's what you use the full posterior distribution for. Well, does that work? So these are the two uses, recovery and quantifying remaining uncertainty. And I'll do this in the case of Gaussian priors. So on this sheet, the only thing changed that now I put Gaussian priors here, and the prior is a Gaussian. Here's an example. I take the logistic regression model. So that's just, we have data, x's and y's, and we have n of them. And the y is a 0-1 variable, and the x is a covariate. We model the probability that y is 1 given x has some value by the logistic transform of theta of x. And in the usual model, you would take a linear function here of x with a few parameters. And now we're doing this non-parametric, so this theta is really an unknown function that we only want to specify up to saying that it has some smoothness or something like that, but no specific shape. The Bayesian analysis that we do here is we put a prior on the theta, and I took, for these two pictures, integrated Brownian motion. Brownian motion is a well-known Gaussian process, and integrated just means taking the primitive, that makes it a little bit smoother, and there's also a scaling factor in front of it. And then I produced these two pictures. Actually, the InLab package produced these two pictures. They have the same data, these two pictures, so the same realization of x's and y's. I just used two different priors. In both pictures, this red curve, that is the true curve. I simulated this data, so I knew what the true was. The black curve is the posterior mean, and with InLab you can also easily produce so-called credible bands, and they're made, that's these blue things, and they're made in such a way that you fix some argument x is one-dimensional here, and then you go to the posterior distribution of theta at x, so marginal posterior distribution. It's a one-dimensional thing, and you can take a central interval in that marginal posterior distribution. Here I took 95%, and that gives an upper upper and a lower bound, and that's exactly the values of the two curves. You do that for all x, and so you get two bands. I took two different priors. Both times it's integrated Brownian motion, but the scaling that I used is different for the two, and you see I get different results. So the prior somehow influences what I get for the posterior. That is not a surprise, but it's even true if n is fairly large, you can have this effect. Now, in the left picture, the bands do contain the truth, so that's something we like. Somehow the posterior captures the truth. The posterior mean is a bit off. The information in the data is not very high, but at least the full posterior will tell you that the mistake you make is not bigger than your distance to the truth. Here, the difficult part of the reconstruction sticks out of the band, so you are kind of off. The question is, can we understand why that happens, and when will that happen, and when will that not happen? Here's a second example. This is, you could say, example from physics. First, we define some function u, which is a solution of a partial differential equation. Here, this is the heat equation, and we have boundary conditions here, and we have an initial condition at time 0. So we have u is a function of space, say, and time. At time 0, the u x0 is some function theta x, and that is our parameter in this problem, the whole function at time 0. What we will observe is the function u at time 1. So we don't see how it develops, but we know it starts at some unknown function at time 0 that we want to know. And at time 0, we observe it with some noise. That will be the data here, will be the function u at time 1 added with some noise to it added. Yeah, so how can we do that? You can write this. A convenient way of doing this is to expand theta in a series with coefficient theta I, basis functions here, which could be the eigenbasis of the operator that's involved here. That gives me exactly the final thing. And then you can say, I just put a prior on theta by putting Gaussian priors on every coefficient in the series expansion. I take them independent for different basis function. There's some parameters, of course, in the Gaussians. I take them mean 0, but there's some parameters in the variance, which I'll come back to later. Then the data is, as I said, the function at time 1, k of theta, I called it here, plus some noise. And these are two pictures that come out, and these are cases where we have small n and large n, and you see that reconstruction becomes better if n is larger. That's not surprising if you have less noise. We also have credible bands, there's these green things, and you see the black one, that's the true one again, and in both cases it seems to work fine. The dashed things here again are some simulations from the posterior. Those were just simulation examples. People in practice, of course, do this all the time, and I took two more or less random examples. This is one from genomics, where there was time here as the index for the function, and its abundance of a transcription factor that one is trying to estimate. The authors in the paper, they produced the credible bands on the picture. And I don't think they asked the question whether that really works. If you just see this, we don't know the truth here, then you think this is highly informative because we have a posterior mean and it is within the credible bands. Well, that's by construction, so there's no guarantee that the truth is really in there, unless we can prove some theorems about that it is generally the case. Here's another example where the function is a surface. It comes from Earth sign, and it's travel times of surface waves. The left side gives the, well, if you do a surface, then it's hard to give these credible bands in a picture, but what is done here, this left picture is the posterior mean. It's a heat map of the posterior mean, so the colors give the height of the surface in this thing, and the right picture gives the posterior standard deviation, so that is your measure of uncertainty in the posterior mean, or not really the posterior mean, but in the posterior distribution. Okay, now in the rest of the talk I'll use the following notation. as usual, we have a prior model, so theta comes from some prior distribution. We have some data, which given the theta has some density p, and then we form the posterior, which is just the conditional theta given by. Nothing special here, that's the same in non-parametric or parametric. We always get the posterior by the usual formula, reweighting the prior by the likelihood. And I'll look at two uses. One is recovery by the posterior distribution. So we take the mean of this posterior distribution and we see if that is close to something that we want it to be close to. And the posterior is used as an expression of uncertainty. And then you're talking about the spread in the posterior distribution. One Bayesian way of doing that is to look at a credible set, which is a set which depends on the data in the parameter set. So it could be these bands around the function. And it's made in such a way that the posterior mass of that set given y is 95%. Well, this doesn't say what sort of set it is, but typically you would take some set surrounding the posterior mean in some way. Now, it's very hard to study that in theory. And so what we're going to do is asymptotics, and I'll have an index n that will express the asymptotics. N will tend to infinity, and n will have several meanings in several examples. Could be the noise level, could be the number of observations, and so on. And then the rest, I make everything dependent on n, and even allowing a prior to depend on n to see what that does. And everything is the same. If you do some studies on this, then you have to become a frequentist, at least partly, because, the posterior is just what you get from your prior, and that is basically end of Bayesian analysis. You can marginalize it and extract all kinds of information, but you cannot say anything whether it is good or bad unless I think you become, at least for the moment, a frequentist. And how do we do that? We assume that now the data is not generated as in our Bayesian setup, first parameter from prior and then data from conditional given parameter, but actually there is a true function, theta naught, out there. So I denote the theta naught, I call it the truth, and the data is generated according to that theta naught. And then you can study the posterior distribution under that sampling distribution of Yn. I'll study two things here, the rate of contraction, and we'll say that rate of contraction is at least some value epsilon n that will depend on everything, in particular on the truth. If this equation holds, and what that says is I need to measure a distance to the truth somehow, and I took a metric d here, could be a uniform distance, so the width of the band, or some L2 distance, some distance between theta and theta naught, and I'm going to look for balls around theta naught of radius epsilon n. And what I like is to find the epsilon n such that those balls under the posterior distribution contain all the mass. Or in other words, the probability under the posterior that the distance of under the posterior from the truth is bigger than epsilon n, the posterior mass outside the ball of radius epsilon n around the truth, that should be very small, should go to 0. Well, this is the asymptotic, so we get an error. We want that posterior probability to be small, and then in asymptotics we can say we will look for the epsilon n's such that the expected value of that goes to 0, or what is the same that the posterior probability goes to 0. In that picture, there will be maybe something like, if this red one for this picture would be the true curve, then and all the realizations are here, then the epsilon n should be somewhere at the boundary of these things, the width of the curve somehow. Then the second thing is, that's recovering. The second thing is uncertainty quantification. The credible region. I defined on the previous slide some set of posterior mass 95%, but we can also look at the frequentist mass of that, and this is treating the credible set as a confidence set, and I calculate its coverage in the frequentist sense. So I look if the yn comes from the distribution index by the theta naught, whether the theta naught is covered by the credible set. A frequentist would call C and yn to be a confidence set of 95%, if that would be exactly 95%. In a more general sense, you might say that the 95% would be nice if it would be exactly 95%, but we don't have to be frequentists. But we would like to make this this credible set to give it some meaning. So if the data gave a credible set like this, it's much more narrow around the curve, then we would want that to mean something rather than this. And so maybe we're not so much interested then in the 95%. You could say, that's frequentist nonsense. But at least we would like the posterior to express the remaining uncertainty somehow. So up to a constant, maybe it should be okay. It shouldn't be completely off. Now, what do the frequentists say here? And it's nice to have a benchmark so that we can look at the posterior distributions, what they do, and compare it to the frequentist world. And you have to keep in mind then for the rest of the talk this rate in n. N is my asymptotical parameter, and I set up the models all the time that the typical rate becomes a power of n, and the power is a bit funny with a parameter beta divided by 2 beta plus d. D is the dimension of the function of the curve, so for a function would be 1, for a surface would be 2. And the beta here is something like the smoothness of the true theta naught curve. This is a typical rate that one gets in nonparametric estimation. Nonparametric theory is very much concerned with estimating smooth functions. So you assume that some true function has a certain smoothness, and then you get this rate if beta is the smoothness. Much more precisely, you get that the minimax rate of estimation of smooth functions has that order, and that I gave here. So we have this discrepancy d as a distance. I squared it, that's often done. And then I squared the rate here as well. You look at the frequent distribution of yn, an arbitrary estimator. So we look for the best estimator, t, for the theta naught. We take the risk, which is this expectation, and we soup it over all sets of truth that are beta smooth with a derivative bounded by something. That's the little 1 here. So theta naught is beta times differentiable, and the derivative is bounded by 1. And we take the soup over all those functions, and then we look for the best estimator. That is the minimax rate of estimation, and that comes out, well, if you square it, comes out as this. And so this is the rate. As beta is bigger, then we assume more on the truth. We assume it's smoother, and in fact it approaches n to the minus a half for beta is infinite. But non-parametric situations, beta will be finite, and so this will tend to 0 slower. Will be harder to estimate. Now, the nicest thing about frequentist analysis here is that one can get estimators t that attain this rate for any beta, even without knowing those betas, and those are called adaptive estimators. Okay, let me turn to Gaussian process priors. A Gaussian process is some stochastic process. Here you see a realization of a surface. It's a Brownian sheet in this case. And so a stochastic process and its distribution can function as a prior. So realization is our model for the unknown function. They're very useful because there are many different types of them. You can model almost any sort of thing with a Gaussian process, and also because you can do computations easily in a number of examples with Gaussian processes. And every prior is reasonable in some way, although tuning by some hyperparameter of a Gaussian process is often desirable. I'll come back to that. Here are some examples. Brownian motion, I already showed you one example. This is one realization of Brownian motion. So you would say, my true function, I think it looks a bit like this. Most people find that very wiggly, and in fact, Brownian motion is not differentiable, so it's true, it's very wiggly. So one way of making it smoother would be to take the primitive function of this, and that's this. You could also integrate it another time, and it becomes more differentiable, and that's this one, and if you integrate it another time, it's this. The striking thing about these 4 pictures, I think, is that the first one, Brownian motion, looks very different from the second one, but when you go 2, 3, 4, if you integrate more and more, you eyeball no difference anymore. It's very hard to judge a non-parametric prior by just looking at a realization from it. These are all nice, smooth curves. The shapes of these curves, they don't mean anything. There's just a particular realization. You sort of look how it changes in space. There are many other Gaussian processes. These are two examples of stationary processes. Stationary means that if you take an interval here in space or time, then the distribution of the process here is the same as when you take an interval elsewhere. Brownian motion doesn't have that because the variance increases with time. This is an example of a stationary that's very smooth. In fact, this is an analytic function. You see it's wiggly, but it is very smooth. And this is an example of a function with smoothness 3/2, so 1.5 derivative, whatever that may mean. And that's coming from the Matern class, which you can do for any smoothness except 3/2. And you see a visible difference here. If I would make this smoother, you would not see so clearly that there is a difference. And here are some other examples: fractional Brownian motion, Brownian sheet. And the series prior that I also looked at already, you take your favorite set of basis functions. Those are deterministic functions, and you add Gaussian coefficients generated from Gaussian distributions that give a Gaussian process as well. Now here's the main result, a main result on posterior contraction, so the recovering, if you use a Gaussian prior. I need a little bit notation. To make this theorem true, we need prior to be a Gaussian map in a Banach space. For Brownian motion, for instance, continuous functions. Could be something else, but in any case, we have some norm that we can measure distances for the prior. It's like the d, but not exactly the same as the d that I had before. Theta naught will be the true parameter in that space. Then the basic theorem is that the rate epsilon n of contraction is given by this equation here. You solve this equation and you go for the smallest solution epsilon n that satisfies this. Now we're looking for the best we can get for this thing, and that goes for the smallest one that satisfies this. That is the rate you get. Well, there is something, of course, I need to say something about what the sampling model is, and for that, at the moment, I have this line: if the statistical distances on the model, on the likelihood, combine appropriately with this setting of the Gaussian process, then we get this equation. What is this equation? Well, this is about a ball around the true function in this particular norm. Could be a uniform ball around theta naught, and this is the probability that the prior gives to that ball, that a realization of the W gets into that ball. That probability should be big enough, which is quite understandable that you get something like that, because you're trying to recover theta naught, so you have to put some mass at theta naught, in the neighborhood of theta naught, so that next, when you hit it with the likelihood can correct the prior to put a lot of mass next to theta naught. If there's no mass at theta naught, certainly the posterior will also never target theta naught. So you need some math. Why you get exactly this equation is a bit harder to see, and I won't explain that. This is called a centered small ball probability. Small because the epsilon n will tend to 0, so this is really about a tiny little ball. I said if the statistical distances on the model combine appropriately with the norm, and I can show you what that means for some examples. Don't want to do all the details here, but for instance, if you do density estimation, you would have arbitrary ID, say in a compact interval, and you might make a density model for that with a Gaussian process prior by taking the Gaussian process, which is a thing that has Gaussian marginal distribution, so it's positive and negative. You want to make it a density, you want to make it positive, so you can put it in the exponent, and then you have to renormalize to make it integrate to 1. So this would be some prior model for the density. Then the theorem is true if the norm on the Gaussian process is the uniform norm, and distance on the parameter, on the densities here, is the Hellinger. Classification, I've shown you how to fit Gaussian processes in classification, and well, there are some distances here as well on the theta that combine with the distance on this. And you can go through other meaningful statistical situations, regression, ergodic diffusions, and other ones, where you have that this theorem is valid if you take the correct statistical distance. So here the Hellinger distance, here some L2 distance, and so on. But I skip the details for that. For inverse problems, and the heat problem is an example of an inverse problem, and I will come back to it. So let me say that the rate equation is somewhat different, and we do not quite understand that in generality, but we have some calculations for special cases that I'll show later. I'd like to first translate this general theorem on rate of contraction with Gaussian priors in the following way. I had one condition, and I make it into two. That makes it more complicated, but it also helps illustrate something about Gaussian process priors. I introduce here the so-called small ball exponent. And what is that? This is the prior mass of a ball around zero. That's the little zero here. It's a ball around zero. Before I had a ball around the true function theta naught, and now I take it at zero. And the prior mass of that ball is here written as e to the minus phi naught epsilon. It's useful to take that exponent because typically that small ball probability is very small, and so it's e to the minus something big, and the big thing is then the phi naught epsilon. Now that thing appears in the theorem. The rate of contraction, epsilon n, should satisfy this equation for the small ball probability. It's the same equation basically as before about the presence of prior mass, but now the truth has been replaced by zero. There's a second equation, because this equation does not involve the theta naught, as you can see. It just involves the prior. And that's the thing I like to explain, that you can pull this condition apart into two. One only about the prior, and the other will involve the truth. Here's the theta naught. Well, the second one is a bit more complicated, and I'm not going to go into details of this equation, but it involves the reproducing kernel Hilbert space of the Gaussian prior. Every Gaussian process has a thing like that. Well, I'm not going to explain what it is, because either you know it already, or you will not understand it in 5 minutes. But let's just say there is some equation here that you have to solve, which involves the theta naught and then the Gaussian prior. It's the combination of the two. And you have to satisfy both. So you get a lower bound for the rate for both equations, one from only the prior and the other also from the combination of the truth and the prior. Let me show you in a few cases what that gives. Suppose I take the prior to be a Brownian motion, this very wiggly thing. Then what is the small ball probability? I try to explain that in this picture. If I take the uniform norm, then the uniform norm, a ball is a band. And I hope you can see there are two red curves here, and everything in between is a small ball. It's a ball around the midline of these two red curves. The small ball probability of Brownian motion is the probability that the Brownian sample path stays inside this band. That's not likely. The realization of Brownian motion that I show you here is not within the band at all. And you can see that it will be unlikely that one will stay in there all the time. It first has to start here, of course, inside. That's not so bad. That's a single Gaussian distribution. And it has small probability because it's a small interval here, but with some probability will start. But then it has to stay there all the time. And Brownian motion is very wiggly, so it wants to get out of that band all the time. Well, it turns out one can compute this small ball probability, and it is e to the minus 1 over epsilon squared. So the exponent is 1 over epsilon squared. E to the minus 1 over epsilon squared. So if epsilon is very small, if you have a tiny band here, then it is going to be very, very small. E to the minus something very large. Now, the fact that that is so small will give you, by the first equation in the rate theorem, an n to the minus a quarter rate, independent of the truth. Whatever the truth is, you will never go faster than n to the minus a quarter with Brownian motion. And that's what you see here. If I take a function theta naught, it's in c beta. That means it's beta times differentiable. It's smooth of order beta. Then the rate is n to the minus a quarter as soon as beta is bigger than a half. So no matter how smooth that function was, I will never get better than n to the minus a quarter. That's very disappointed, because for a very smooth function, I told you before, the rate in nonparametric estimation is n to the minus beta over 1 plus 2 beta, and that approaches n to the minus a half. You go to the parametric rate if the beta is really large. It doesn't help in this case to make the beta larger. You never get past this slow rate. If the beta happens to be very small, then you also punished, you get n to the minus beta over 2. And in fact, if you compare it to this minimax rate, n to the minus beta over 1 plus 2 beta, which is what you can get with a kernel estimator or a wavelet estimator or whatever, then you get the optimal rate only if beta is a half. And a half, in a way, is the smoothness of Brownian motion. So what it says then is simply that if your prior says truth is smooth of order half, then you do it correctly for a truth that is also smooth of order half, but you don't do it well for other truth. In particular, smoothness doesn't help, which is very, very disappointing from a non-parametric estimation point of view. Okay, but Brownian motion is a very rough thing, and we wouldn't like that as a prior anyway if we wanted to estimate a smooth function. So let me take the integrated Brownian motion, let me integrate it alpha minus a half times, then becomes alpha smooth. Brownian motion is a half smooth, so if I integrate it alpha minus a half times, then I get alpha smooth integrated Brownian motion. That's exactly right if your true function is also of smoothness alpha, if it matches, and otherwise you get something which is suboptimal, but it is like this. Small ball probability is now bigger, and you can see that from this picture. Here is the sample pass. It's not in the small ball, but you can easily imagine, since the sample pass is much smoother, if it starts inside, then there is more probability that it stays inside because it is smooth and it tries to go on smoothly. Other example are stationary processes. You can make stationary processes by setting up the covariance function with some spectral measure like this. And I'll look at two particular examples. One very smooth one, which has a spectral measure, a Gaussian measure like this. That gives very smooth sample path. And then we get these rates here. And they are best stated in terms of the Fourier transform of the true parameter. And I'm in d dimensions here. There are two cases. If the true parameter is very smooth itself, like the prior, you get a very nice rate near 1 over root n, which is not non-parametric almost anymore. The near means there's a log factor missing there from 1 over root n. So you're doing very well, as if you have a finite dimensional parameter that you're estimating. This is a condition on the Fourier transform to say that the theta naught is very smooth. If, on the other hand, the true function is beta smooth, and in terms of the Fourier transform, that would be a condition like this, then the rate is not even a power of n, but it becomes a power of 1 over log n. So you're severely punished by taking a prior that is really good for smooth functions. Then you're severely punished if the true function is actually not super smooth. Then everything gets lost, you could say. You get hardly any convergence, while you could have a power of n there, but you get a power of 1 over log n. Then these other classes, the Matern, they were somewhat less smooth, and you can adapt the smoothness. If you take the alpha here, then it becomes alpha smooth. This was the 3 over 2 smoothness. And that will be exactly right. You all have the exact match. If alpha is beta, then the Matern is right. Now, in practice, maybe you would scale the priors. So let's look at scaling the priors in time and in space. You could, if you want to have a prior for functions on 0, 1, what you could do is you could take a process and you could run it for a little while and then pull it out like this, scale it up so that it covers the complete time set. Or you could maybe run a prior Gaussian process for a long time and then scale it in so that you have a function on 0, 1. And you see in the picture that, well, certainly here you see very smooth here, and if you scale it becomes somewhat rougher. Not in an analytic sense, the number of derivatives doesn't change by this operation, but in a Bayesian sense, it does, in fact. And here also the smoothness increases. So if we do integrated Brownian motion and we scale that in time, then it turns out that you can do a scaling factor depending on n here, and the scaling factor depends also on the true target smoothness of the prior. And then you get a prior scaled integrated Brownian motion, which gives the optimal rate for any true function up to smoothness beta. Yeah, the drawback is that you need the beta to do this particular prior. But in any case, there is a scaling that works for any theta. Well, up to k plus a half. If this is k times integrated, you can go to k plus a half, sorry. K plus 1, not k plus a half. Not very smooth, but you can get... So stretching can help a little. You can go up to k plus a half. Shrinking, that goes the way down to 0 for smoothness. You could also start with this very smooth Gaussian process, and then basically you would only want to shrink it so that you make it rougher. And it turns out there is indeed also a scaling there that makes it right exactly for a beta smooth truth. With this scaling factor, you get the right result. So scaling does change everything, and shrinking a super smooth seems to be a very nice way of getting a good recovery with your prior. Now, the scaling factors, they depend on the true smoothness beta, which we don't know. And, well, maybe you're willing to guess, say that it is 2 or something else. But if you cannot guess, then you probably want to do something else. You might want to do the scaling based on the data. That's called adaptation. So we could try adapt a prior to the data in 2 ways, by the hierarchical Bayes method or the empirical Bayes methods. By the hierarchical Bayes methods, I would take a scale of priors, maybe of several smoothness levels, and then I would put a prior on the smoothness level, or maybe on a scaling factor, and then do full Bayes with, it's not a Gaussian prior anymore because it is a mixture of Gaussians, but in any case, that gives a full Bayes method. Empirical Bayes, you would get the regularity from the data, and a typical method is to take the marginal distribution of the data, so integrating out the prior, leaving in the smoothness there, and then optimize maximum likelihood estimator on the smoothness, and then we use that data-determined smoothness. Well, the hierarchical Bayes thing, we know quite a bit already. It works in some generality, many different ways of setting it up. The empirical Bayes, we actually know very little except some examples. I'll give you a nice example of the hierarchical Bayes approach. This works in this way. We choose a gamma. Well, we choose a scaling factor. In fact, the d power of the scaling factor from a gamma distribution. I take this very smooth Gaussian process, and then I scale that with the random scale coming from the gamma. So I take a d's root of a gamma distribution. And it works in quite generality. If you have a smooth, beta smooth truth, beta derivatives, then indeed you get the minimax contraction rate with this mixture of Gaussian processes. So nearly n to the minus beta over 2 beta plus d. Also, you keep the nice properties of theta not as super smooth, then the right scaling or no scaling got you nearly n to the minus half. You still get it with the scaling. So the scaling doesn't, the random scaling doesn't confuse, the full Bayes random scaling doesn't confuse the prior. And that's a very nice result in Bayesian non-parametric estimation, because it means a full Bayes approach can solve the bandwidth problem, because what we are choosing here is the smoothness. That is the typical bandwidth if you do a kernel estimator or a series estimator. It's the truncation. And you can do that in a fully Bayesian way, for instance, with this scheme. So, summary of recovery. The recovery is best if the prior matches the truth. A mismatch will slow down, but it will not prevent recovery. You will get some convergence rate, but it may be very slow. It can be prevented, this mismatch, by using hyperparameters. And then I get into the credible sets. This is just my notation. I'll just remind you of what I call the credible set. I have the posterior distribution, and then credible set is a set in the posterior, typically taken central around the posterior mean, that has 95% of the posterior mass. And we'll look at the coverage of this credible set by treating the credible set as if it were a confidence set in the frequentist sense. So we look at the coverage in the frequentist set. There's an early answer to this question, whether that works or not, and the answer was it doesn't work. This is a paper by Dennis Cox from 1993, and he looks at a particular regression problem. It's a bit difficult to read this whole paper. It's very clever, very smart, but his conclusion is rather terrible. That's what he says. Non-Bayesians often find such Bayesian procedures, that's the credible set, attractive because the frequentist coverage probability of the Bayesian regions tends to the posterior coverage probability in typical cases. It was my hope that this would also hold in a non-parametric setting. So in a parametric setting with finite dimensional models, everything is fine. And we all knew that before 1993. And Cox said, well, I hoped it was also true in a non-parametric setting. Unfortunately, the hoped for result is false in about the worst possible way, visibly, this equation. And what does it say? Here it's the coverage, and you see that the lim inf of the coverage is 0, which is terrible. There's no coverage at all, which means no correct uncertainty quantification. Not only that you don't get 95%, which we could live with, I think, so 95% is rather arbitrary, but you just get 0. When do you get this? You get this for all the theta naught that you sample from your prior. So that seems terrible news, and it's strange that this paper hasn't been quoted before and that we're still doing non-parametric estimation without really investigating this further. Cox model can actually be cast in a simpler form. It's a sequence model where the function is developed in an infinite series with a fixed set of base functions, and the theta i's come from Gaussian priors, as I talked about before. So the data then become just independent observations on these coefficients, and each coefficient is measured with a variance of 1 over n, an error variance of 1 over n. And I also have a multiplication here, ki, that is a known number, could be 1. In the case of Cox, it is 1. So the observation has mean kappa times theta I. We put a prior on theta, which are just independent Gaussians with some variances that will tend to 0 typically, because we have infinitely many of those. Now, to make that a bit more easy to read, we'll just say that the data is some infinite dimensional Gaussian. It has a certain mean, that's a function of theta, and it has a certain variance, which is essentially 1 over n. They're independent. And the prior is also an infinite dimensional Gaussian. It has a certain covariance, lambda. Then, if you see those two equations, you see it's just conjugate. It's just the mean here. The k is actually linear, so you can work out what the posterior is. In that case, the posterior is also Gaussian infinite dimensional, and you have to multiply the data with some matrix, some operator here. The formula is given here, but it's of no importance for us. It's just a linear transformation on the y, and it's going to be some posterior spread, posterior covariance, which are called S. The formula is there, but has no importance for the talk. What is maybe interesting is that but not surprising, the S is not data dependent. So the data is in the posterior mean. The posterior spread is just some fixed covariance. Then the credible set in this case you would make, that's what Cox also looks at, is to make a ball around the posterior mean, and then you would give that ball a radius such that the radius makes that if you take a centered Gaussians, then the ball has exactly probability 0.905. So that is a credible set for 95% level in this situation. So it's a pretty simple setup. To see what we get, I'll show you results for truth and priors. The truth, again, I will have the parameter beta, which gives the smoothness of the function. In this case, I'll measure smoothness with the Sobolev space. That is this. So the theta, the true one, is a series expansion where the coefficients, if you multiply by, if you square and multiply I to the 2 beta is finite. It's basically regularity beta as before. And the prior then, we have a variance here to play with in the prior. We'll take the variance to be 1 over I to the 2 alpha plus 1. And by doing these two things, what I get is as before, I can compare the alpha and the beta. If the alpha is the beta, then roughly you can say the prior and the truth match. If alpha is bigger than beta, then the coefficients under the prior go to 0 faster, the variances tend to 0 faster, so the prior over-smoothes. And if alpha is smaller than beta, then the prior under-smoothes the truth. So the interpretation of alpha and beta are exactly as in the first part of the proof. I'm not being completely precise in the sense that this norm here, which is a Sobolev norm, sometimes you should take the soup, but I will not make that difference here because then it becomes very complicated. Now, first we can talk about the contraction rate in this case. There's nothing very special about it. You get the contraction rate, which is the optimal minimal max rate. There's a little p in here now also because it's an inverse problem. So the inverse nature is the k is 1. If p is 0, then the k's are just 1. But then the contraction rate is exactly as I had before. It's optimal if prior and truth match, and otherwise it's suboptimal. But you always get contraction. So whatever you misspecify, it still works in a sense. Now let's look at the credible sets and let's look at some pictures first. And I show you some picture for an inverse problem, this particular inverse problem. It's called the Volterra operator, which is just the primitive function of theta. So theta is my parameter, the function that I want to estimate. We take the primitive function, and then what we observe is, well, actually an integral of that. This is the physicist notation. The derivative of our data, that's the little dot here, is that primitive plus some noise. So we want to recover a function from noisy observation of its primitive. It's an inverse problem, very nonparametric. And it fits in the sequence series, and you can work out what the expansions are, but let's not look at that. Let's look at the picture. Here are 10 pictures. The priors in the 5 pictures on the left are the same, and the prior in the 5 pictures on the right are also the same. And they're just repetitions with multiple data. So every one of the 5, I generate the data and then did the Bayesian machine in the same way, the same prior. The black one here is the truth. Seen that one before, but it was red, but now it's black. And the red one is the posterior mean, and then you see the wiggly things are things generated from the prior. So it seems to work quite well here. Well, in a sense, we don't have enough data to get complete recovery. That's why the red one is not the black one. But the uncertainty margin given by the posterior, suggested by the posterior, is such that we know that we may be off by that much. And that is true if you repeat it in the data every time. On the right, it's different. You can see that, well, the red estimate is not that much worse than it is on the left, but the confidence bands have shrunk quite a bit. Everything I generated from the posterior is quite smooth, and here they failed to cover it here. There's a big part that's covered here. This whole thing sticks out of the confidence band, and so on. So here the prior is very smooth, and we do not cover the truth, which is somewhat discomforting because the posterior is all we will have. We generate from the posterior, and then we hope that these dashed things give you some sense of how far you might be wrong with your thing. Is it dependent on the amount of data I have? Well, if I take a bigger n, so less noise in the data, then it doesn't change dramatically. In fact, here in the smooth case, it gets very bad because the credible bands here are just shrunk within the resolution of the picture to the posterior mean, and we're missing completely the true curve. The posterior thinks that it's very sure that the truth is right on the posterior mean, but it wasn't. It's the black one. So we seem to have a problem. Can we do some math on that? Yeah, we have this particular theorem. So the situation is this linear inverse problem, and then we had a posterior which was Gaussian, and we made a credible set as a central ball in the Gaussian posterior. Then the theorem goes like this. We have a prior that had a smoothness alpha and a truth that has a smoothness beta. Now, if alpha is smaller than beta, so if we undersmooth the truth, then we do have coverage, and it's 1 uniformly. So it all works nicely, maybe even too nice, because we didn't get 95%, but actually we got 1. If we have an exact match, then it becomes a bit complicated. Any coverage within 0, 1 occurs, but if you don't take the 95% too serious, then nothing terrible is happening. You sort of get the right thing. However, if the prior is smoother than the truth, the right set of pictures, then things are disastrous for some beta smooth one, not for all one, because if it's beta smooth, it can be much smoother. But there are things that are exactly beta smooth that are over smoothed by this prior, and then the asymptotic coverage is 0. That is what you saw in the right picture. We have too smooth a prior, and everything goes to pieces. The posterior thinks it can be very sure of where the truth is, but it is absolutely wrong. It's the prior that told it to be sure, but the prior was wrong relative to the truth. The good news is that in these two first cases, the credible ball also has the correct order of magnitude. So drop this thing about the 95% and what the coverage is exactly. You could look at whether the size of the ball is sort of right. Up to constant, it's always right if you do not oversmooth. If you oversmooth, then you get too narrow balls. Where does Koch's result come in? Well, it doesn't follow from this theorem, but can be explained from the theorem that truths generated from an alpha smooth prior, they belong with probability 1 to smoothness things of smaller smoothness, but they don't belong to this alpha smooth set. And that's why it can be in the third case that you get coverage 0. Now, I'm skipping this for reasons of time. Well, this is about rescaling. I do very briefly. You can also rescale these priors with a scaling parameter here and see if you can repair it. In the contraction rate business, we could do that. I won't go through the theorem, but I'll show you the pictures. If you do a rescaling, then you can get it right after all. And this is for deterministic rescaling. So, credible sets, the first summary. In a nonparametric setup, the prior is not watched out by the data. For recovery, we saw that the prior influences the posterior contraction rate, but you get consistency for most priors. It can be bad, but it is not too bad. You always get something. For the uncertainty quantification, it can be disastrous. And that happens if the prior mistakes the truth for being more regular than it is. The posterior will then be too concentrated and center far away from the truth. So both ways it does it wrong. One solution to that would be to undersmooth, so take a prior that is not smoother to the truth. That would require that you know something about the minimal smoothness of your true function, and then you can fix the prior to that. Now don't undersmooth too much, because then the contraction rate, though it still will be something tending to 0, so you do get consistency, but the recovery will be slow, so you should not undersmooth too much. I finish with this part by saying that much work to be done. I showed you results for the linear inverse Gaussian problem. We also have some results for Gaussian regression, but there's many things to be asked. And this is the heat equation problem, just again to show you that there might be trouble. You see priors that increase in smoothness, and here it's still okay, here it's still okay. Here you get in the priors that oversmooth, and here they're very oversmoothed. And this is for a bigger N, but the message is the same. My final part of the talk will be about adapting credible sets to the data. For recovery, we saw that if your prior is not matching the truth, you can make it match the truth by using a hyperparameter. And you could do that in a hierarchical empirical Bayesian setup. How does that work for credible sets? Does it also work that well? Skip that. Again, I'll work in the linear Gaussian inverse problem, and we actually have no results for the general Gaussian situation, though I don't think it will be very different in general. So the same setup as before. So we have the data from this infinite Gaussian, we have a prior, we have a covariance where I now made the alpha explicit, that is the smoothness of the prior. It's the rate of decrease of the eigenvalues of the lambda, it's the alpha. We get the posterior, we also made the alpha explicit, and we can, for a given alpha, take the credible ball. Now suppose that we determine an alpha based on the data using the empirical Bayes method. So for that, you get an alpha hat, the estimate, by saying that yn for given alpha if you take theta is Gaussian, yn given theta is Gaussian, then yn marginally has a Gaussian distribution, which is mean zero and has this covariance that contains the alpha. And then you do maximum likelihood on the alpha in this model. If you work that out, it's this thing. It's kind of complicated with an infinite series, so it's not very obvious to analyze, but it can be done. It's quite explicit in this situation. Anyway, empirical Bayes here takes the alpha data dependent based on marginal maximum likelihood. This works for recovery, but I will not present results. The question is, does it also work for uncertainty quantification? And more precisely then, if I take the ball that you had for a given alpha, and if I stick in the alpha head there, does that cover? So determine the alpha based on the data and then take the... Here I do empirical Bayes. We believe at the moment that hierarchical Bayes, where you put a prior on alpha, will give similar results, but well, we haven't written that completely out. Counterexample. Horrible, doesn't work at all. Credible sets can be terribly wrong in this empirical Bayes situation. And this is the pictures that I started with. Now we had a black truth, we had a blue posterior mean, and in gray we had posterior credible bands, 95%. Last picture works, and what is different here is the informativeness of the data, the noise level. Here is the n is small, there the n is big. The truth is the same in all four pictures, and the data is regenerated, of course. And these are two intermediate values of n. You cannot, it doesn't work. You can see that the two middle ones, they're terrible, and it seemed to be an interaction between the noise level and the truth in this case. For another truth, for other values of n, it might go wrong. What this is a counterexample of a truth. So it's a particular function that we took, the black one, and for that, this particular procedure goes wrong for these values of n here. We can make other counterexamples, but there are also truths for which it does work. Let me, for the last 5 minutes, try to see where this comes from. First, what do the frequentists say about this? They have a concept of honesty of confidence sets. Honesty means that the coverage is at least 95% for any possible true theta naught, for all, so uniformly in the truth. So theta naught here should contain all possible truth, all truth you think might be valid. Could, for instance, be a Sobolev ball. Then it's a known result that if you know the beta, you want to be uniform over all functions with beta derivatives, you can get confidence sets of, honest confidence sets of the estimation rate enter minus beta. There is a problem though, if as soon as you allow more than one smoothness level, here all smoothness levels bigger than some lower bound beta naught, then the diameter of the confidence set necessarily will have to involve this biggest, the biggest model, the smallest smoothness beta naught. So there is something nasty going on here. If you want to be honest over everything, here everything smoother than beta naught, then you get a diameter that cannot adapt really to the beta. It's determined by the biggest model. It's a bit complicated thing here. There's some other ways of describing this, depends a bit on the metric, but I will skip all that. So there is a difference in frequentist literature between adaptive estimation and uncertainty quantification. If you do adaptive estimation, there is a success story that starts in the 1990s with the wavelets and so on. A more regular true function is easier to estimate. It should be. There's less degrees of freedom. Estimators can then be simultaneously optimal for multiple regularities. You don't have to know that it has 10 derivatives. You can just do that adapting from the data. And Bayesian estimators, we now know, since a couple of years, can also achieve this by prior on the bandwidth, on a bandwidth parameter of the problem. So that is a success story. You don't have to know the smoothness. You can still do very nice things. Uncertainty quantification is very different. Honest uncertainty quantification must argue from the worst case, the smallest possible regularity level. And you cannot adapt so much to the smoothness. As Lucien Berger phrased it in a discussion here, adaptive estimators from the success story, they do the best that's possible in view of the properties of the underlying function to be estimated. That's quite satisfactory, but the estimator does not tell you how well it does. You have no idea about the order of magnitude of the distance. So you're doing well, but you don't know how well you're doing, and so you cannot really give the uncertainty margin on your estimator. And that seems to be in the nature of things. This is an attempt to solve that problem by looking only at particular truth, and they're called self-similar here by this complicated equation. You say something about the Sobolev norm high up at higher resolution levels should satisfy a lower bound. The interpretation is that the truth has the same character at any resolution level. And very vague idea is that if you have a noisy data set, you can estimate the function only up to a certain resolution level. You could say there's something like an effective dimension where you can still do it with that data, and above that you cannot do it. And self-similar sequences are the same at every possible effective dimension. And for those, you can get frequentist, nice, uniform, honest confidence sets. And the good news is that you can also get good Bayesian sets that adapt for those truth with empirical base. So for those sequences, a special class of sequences, it works. And you see that in this picture. This one was just the prior matching the truth, and here I scaled the truth, and it suddenly has credible bands that do satisfy it. And this true function, the black one, is a self-similar one. That's a nice one. Where do then these problems arise? Well, this is the Cox result again, where you got a 0. Well, the first thing you might notice in the paper is that if you would blow up the credible set a little bit, just by a log factor, you suddenly get 1 instead of 0. So blowing it up works. And then I have the conjecture, which is about where I'm going to finish, that in the Bayesian adaptive sense, there is something similar true, and you can do it for every alpha at the same time with the empirical base alpha set. Honesty is questionable in this case. So then where does this go wrong? Well, this truth is not self-similar, and what actually, this was a very smooth truth, the beta 0, and you could say that the black one is unlike anything that is sampled from some prior that I used. I used a whole scale of priors with different smoothnesses, but this one was actually smoother than any one. It had sequences that were non-zero up to some level, and then all zeros, and none of the things that come from the prior have that. And it seems that that is bad news. But I have difficulty interpreting what it really means. So here are then conclusions and conjectures. Non-parametric credible sets are never correct frequentist confidence regions. Priors that undersmooth the truths give a reasonable idea of the uncertainty in the posterior mean. If the prior oversmoothes the truth, then the spread in the posterior is very misleading about the remaining uncertainty. And that effect may disappear if the prior is scaled, for instance by hierarchical empirical Bayesian methods, but only for truths that resemble the prior. At least so we think at the moment. And then finally, it seems then that we must either undersmooth or believe the fine details of the prior. And is that possible in nonparametrics then? I make it open-ended. I show you the picture again. Can you believe when you see these priors that one of those is really the best for your data, or do these three, for instance, look exactly the same? Is it really possible to know what you're doing in nonparametrics? So I keep it with that question. Thank you very much.
Thank you, Ad. So there's time for some questions if there are any. There are microphones down in front. If you'd like to ask a question, please come down. Maybe I could ask briefly about the favorable case, the recovery. The full Bayes handled the problem, and I noticed a gamma distribution means stuck in there at the top, and I assume that this can't be true for all distributions, but I assume gamma is not needed. Can you tell us what the story is there?
Yeah, I can. In fact, it is true for all gammas, so all the parameters. Then we have to realize it is asymptotics, and in the asymptotics, the parameters of the gamma will not come true. And you do select the correct bandwidth, but then maybe at higher order you would have to fine-tune that for your data. Yeah.
Thank you. Next.
I had a question about one of your slides where you said shrinking with the super smooth can adapt it to anything. I was wondering what's the relation between shrinking the super smooth, by which I think you mean the squared exponential
Yes.
Gaussian process. What's the relationship between shrinking it horizontally and just taking a smaller horizontal length scale parameter, L?
In this case, I think it's very different. In the integrated Gaussian case, it would be the same because it's self-similar, but here I think it is different. I don't know what would happen if you would scale the vertical thing here.
Okay.
I don't think it will work, but I don't really know. Oh, I shouldn't have said this because it's all taped, but...
And just quickly, one of your main conclusions was about oversmoothing. And can I take that to imply that if you use a squared exponential covariance, which is infinitely smooth, then you, in some sense, for uncertainty quantification, always miss the truth unless you have, as you say, excellent reason to know that the truth really is beta infinity?
I think the answer is yes. So if you do not rescale the very smooth Gaussian process, I think that the credible sets will be completely off. But we have no mathematical proof. We only have some proofs of this fact for a few typical examples, but this one we haven't handled yet.
Thank you.
Okay, time for one more question. Karen, no, there's a line. No, hang on.
I'm sorry.
In front of you in the line, please. Yeah.
I'll try to keep it short. Your results made me wonder about the possibility of defining the rate of contraction and defining coverage not relative to the true theta, but relative to a theta that's in a class that has smoothness as specified by the prior, but is close to the true theta in some sense. And I wonder if you've thought about that.
Yeah, you might have a very good idea. We have thought about it, but we don't know how to make that precise and to do with it yet, but that might be a good idea. In the contraction rate, that is more or less included because you always look for something in say, the support of the prior that is at a certain distance. But the credible sets, yeah, it is about the formulation of what can you derive really, what can you learn from the posterior distribution? And maybe it should be phrased in the sense that some approximation of the truth is within the posterior support somehow. Yeah, but we have thought about it, but we don't know how to formulate it at the moment.
Okay, let's give one more round of applause for Ad. Thanks for the great talk.